Right now, as we speak, in 2026, we are living through what is arguably the most unprecedented era of solar system discovery in human history. We are literally redrawing the map of our cosmic neighborhood. We've got two of the most powerful tools in the history of astronomy operating at the exact same time, and the data they're beaming back, it is completely upending some of our longest-held scientific assumptions. So, if you want to understand what's actually happening out there in the dark, uncharted edges of our solar system, well, you are definitely in the right place. Let's dive in.
Okay, brace yourselves for this number for a second. 11,000. That is the staggering amount of brand new space objects a single machine found out there in just a month and a half. Think about that. Human beings had absolutely no idea these things even existed. We aren't talking about finding a dozen rocks or even 1,000. 11,000 objects just sitting right here in our own cosmic backyard, scooped up in a matter of weeks. It's the kind of mind-blowing fact that completely resets our entire understanding of just how much stuff is still hiding out there in the dark.
So the machine pulling off this absolute flood of data is the Veresi-Rubin Observatory, perched way up there in the Chilean Andes, over 2,600 meters above sea level. And its main job is this thing called the Legacy Survey of Space and Time, or LSST. The whole concept is brilliantly simple, honestly. Rubin isn't squinting to find one specific object. Instead, it's using this massive, wide net approach. It's basically photographing the entire visible southern sky, over and over again, every few nights for the next 10 years. If anything out there moves, flickers, explodes, or just randomly appears, this system is going to catch it.
To really wrap your head around the sheer scale of this, let's put it into perspective. In the entire preceding 200 years of human astronomy, 2 whole centuries of people staring up at the night sky, we documented roughly 1 million asteroids total. Scientists are fully expecting the Rubin Observatory to find another 1 million asteroids in its first year alone. One machine in 12 months, matching 2 entire centuries of human discovery. There is just no doubt about it, this is the most powerful solar system discovery engine we've ever built.
But the real question is, what exactly is this machine scooping up in all that data? Well, tucked into those first 11,000 objects were 33 new near-Earth objects, meaning 33 space rocks currently crossing paths with our planet's orbit that literally no one was tracking before this year. And then, looking way out past Neptune, it found 380 trans-Neptunian objects. These are basically icy leftovers. Think of them as frozen fossils from the birth of our solar system 4.5 billion years ago. Every single one of these frozen relics gives us crucial clues about how our giant planets physically shifted and rearranged this massive disk of icy debris back in the early days of the solar system.
And this, right here, brilliantly illustrates why scientists are calling this project the greatest cosmic movie ever made. Because the tech making this happen is just mind-boggling. Rubin's camera is the largest digital camera ever built for astronomy. It's literally the size of a small car and weighs roughly 3,000 kilograms. When this thing is running at full capacity, it's going to generate up to 7 million alerts and around 20 terabytes of raw data every single night. It's effectively acting as a giant security camera for the universe, giving us a real-time cosmic time-lapse of everything orbiting our sun.
Now, Rubin isn't just cataloging space rocks just for the fun of it. The early data actually identified and, more importantly, corrected a pretty dangerous flaw in our existing planetary defense catalogs. You see, our tracking systems, the ones we rely on to monitor potentially hazardous objects that could, hit Earth, they had this baked-in positional bias of about 20 to 40 milliseconds, which might sound like nothing, right? But it was a consistent error. Rubin's data has completely eliminated that bias, so this telescope is actively directly making the safety systems we use to track dangerous near-Earth objects so much better.
All right, so while Rubin has been busy casting this massive, ultra-wide net across the sky, there's another totally remarkable telescope that's been doing the exact opposite, zooming in on one very specific target. So let's pivot for a second from the wide survey of the outer solar system to the incredibly deep precision of the James Webb Space Telescope. Because Webb just solved a massive, decades-old mystery, a mystery that astronomers playfully refer to as Saturn's broken clock.
Follow this timeline with me for a minute just to understand the pure hair-pulling frustration planetary scientists have dealt with here for 40 years. Ever since the Voyager flybys way back in the 1980s, different instruments kept returning wildly conflicting spin measurements for Saturn. It was this nagging inconsistency that just stubbornly refused to make sense. The planet looked like it was just casually speeding up and slowing down its rotation. And for 4 decades, this puzzle just sat there, totally unsolved. That is, until 2026, when James Webb finally mapped Saturn's atmospheric auroras and completely cracked the case.
So how did Webb actually pull this off after 40 years? It all comes down to a factor of 10. The James Webb Space Telescope is literally 10 times more precise than the earlier missions. The older measurements had these blurry, built-in uncertainties that were just way too fuzzy to catch the incredibly subtle temperature changes happening in Saturn's atmosphere. But Webb's insane precision, it finally allowed scientists to map out these highly localized patterns of heating and cooling, which completely untangled the planet's actual physical rotation from the wild weather systems just riding around on top of it.
Let's break down exactly what Webb saw, because it's fascinating. Saturn's spin wasn't changing at all. What we were seeing was a massive weather cycle totally masquerading as a change in the planet's rotation. Here's how it works. Saturn's huge northern auroras actually heat up the upper atmosphere, which kicks up these powerful high-altitude winds. Those winds then generate electrical currents, which, get this, loop right back around to power the auroras all over again. It's this continuous self-reinforcing weather loop miles above the clouds. Generations of scientists were trying to measure a changing planet's spin. Actually, scratch that. They thought they were. What they were really measuring was this shifting weather system.
To really wrap our minds around these gas giants, scientists have to combine their tools. Comparing data from the Hubble Space Telescope with James Webb is honestly kind of like slicing through a giant cosmic onion. Hubble gives us the visible outer layers, right? Showing off the beautiful, subtle color variations across the planet's bands in surface storms. But Webb sees an infrared light. It peers deep down into the churning lower atmosphere, and it highlights these deep glowing rings made of highly reflective water ice. Using both of these together lets scientists analyze multiple layers of a planet at the exact same time.
And solving Saturn's broken clock isn't just a win for one planet. It represents this perfect partnership of data that could honestly rewrite our understanding of the entire outer solar system. Because think about it, if these self-sustaining aurora and wind loops are happening on Saturn, the very next question you have to ask is, does this happen on the other gas giants too? I mean, Jupiter, Uranus, Neptune, they all have massive auroras. Figuring out Saturn might actually be the ultimate skeleton key to understanding the weird weather and rotation anomalies on every single gas giant in our neighborhood.
Which brings us perfectly to the grand synergy of modern astronomy. We have the Vera C. Rubin Observatory acting as the ultimate wide net, relentlessly scanning huge swaths of the sky to flag anomalies and spot anything moving. And on the flip side, we have James Webb acting as the ultimate magnifying glass, a hyper-precision instrument that stares intensely at one specific target to tease out the finest details imaginable. Basically, Rubin flags the mysterious unknowns way out near Uranus and Neptune, and then Webb zooms in to figure out exactly what the heck they are.
And the best part? This era of discovery isn't some distant historical event. It is happening tonight. Rubin's highly anticipated Data Preview 2 is expected to drop literally any week now. We could be staring down a massive new wave of outer solar system discoveries as the observatory fully ramps up to those 7 million nightly alerts. Meanwhile, Webb's mission spans decades, and it's already gearing up for the 2030s, waiting for Saturn to transition into its southern spring so we can finally get unprecedented views of the planet's totally uncharted southern hemisphere.
We are truly not waiting around for the next big space discovery anymore. It's happening on autopilot, right now, every single night as we sleep. So as we wrap up this explainer, I want to leave you with a thought. Knowing that Rubin is about to flag millions of moving objects a night, and knowing Webb is standing by to zoom in on them, what do you think we're going to find first? Could it be a new moon hiding in plain sight? A rogue comet on a brand new trajectory? Or maybe something entirely new that doesn't even fit into a category we know yet?